Hey guys, and welcome to one more episode of Builder Nation. For today's agenda, we have Dr. or Professor Jivko Sinapov. He's a professor in the Computer Science Department at Tufts University. His focus right now is on how robotics can learn from and operate within human environments using multisensory perception. So welcome, Dr. Professor. Super excited to have you here.
Thank you so much for having me, Lisa.
I think this is going to be, just like I was telling you, really interesting. And we would love to hear about your professional life, just like I was telling you. How did you get into robotics? But before we get ahead of ourselves, why don't you start by introducing yourself?
Hi, everyone. I'm Jivko Sinapov. I'm an assistant professor at Tufts, and I lead the multimodal interaction, learning, and perception laboratory here at Tufts. So like Eliza said, I'm very focused on how robots can use multiple sensory modalities and interaction modalities so they can be better partners to humans in our environments.
Straight to the point. Thank you. Thank you, Professor. And how do you, what was your first approach? Because I noticed that you're not an engineer.
Mm-hmm.
So how do you get into the world?
That's a very good question. You're right. I don't have professional engineering training. Although in robotics, you have to do some engineering. You have to build things, you have to put things together, both in terms of hardware, in terms of software, and in terms of experimentation. So everything I know about engineering, I know by failing and by doing it the wrong way the first time. But most of my training is that from a science, in computer science specifically, where we essentially try to investigate. For me, one of the most important questions is, what is intelligence, and can it be physically implemented in a device like a robot that can then operate smartly in our environments?
What is intelligence? I mean, for all of our audience, that's a question.
Even philosophers don't agree, brain scientists don't agree. So yeah, what is intelligence? How do we start trying to even think about the question of what is intelligence? Luckily, I'm not a philosopher and I'm not a psychologist, so I kind of just look at their work and look at brain and cognitive science work to try to figure out what are some sort of key properties of intelligent organisms in terms of adaptation and learning. How do they develop over the development of the biological development of an organism? And how can we maybe mimic them in robots to some degree?
If I were to ask you, what is intelligence? Maybe in one sentence.
In one sentence, make sense of the world around you and adapt to it as needed. So the ability to make sense of things and adapt to them as things change. So right now, we do have machine learning, and a lot of other technologists have developed very powerful methods that, for example, may enable robots or drones to recognize things in the environment. But they cannot adapt very well when the environment changes, when something new happens, or when something happens that the engineer did not foresee. Technically, our systems still tend to be quite dumb. They may be quite smart in the areas where they're designed for. In all other areas, they become very dumb very quickly.
Oh, that's really interesting. I mean, you made it sound so easy, but I'm pretty sure that it wasn't at the beginning, especially since you studied computer science. How did you started into research, and then how did you realize that it was robotics, your path?
That's a very good question. So when I first started grad school, or rather when I was applying for graduate school, I did not know what I wanted to study at all. I knew it had to do something with artificial intelligence, so I had some motivation to do work in AI, but I wasn't sure about robotics at all. I mostly already had a software engineering position, and it was okay, but I thought, well, I didn't want to learn more. I want to learn a few more things before I start actually building software. And I think what got me into robotics was I went to a conference called Epigenetic Robotics. I think it was somewhere in Indiana. And one of the speakers was Cynthia Brazil. So she is a very well-known roboticist and scientist in our field. And when I saw her speak about her trying to build a robot, I think it was Kismet was the robot's name. I was like, wow, I really want to do that stuff too. So she was kind of one of my inspirations initially to get into robotics.
Really good. And that was before your PhD?
I think that was my first year of my PhDs when I went to that conference. So it must have been 2007, 2006. I don't know.
Oh my God, that was
it's so long ago.
And then you started, you finished your PhD, and then you did...
The PhD, I took a while to finish. It's supposed to take 5 years. For me, it took me 7.5 years just because I was having a lot of fun. And usually after a PhD, oftentimes we would do something called a postdoc position. So a postdoctoral associate where you work in another lab. So I went to UT Austin to work as a postdoc. with Peter Stone and a few other professors there. And then from there in 2017, I basically decided, okay, I'm ready to lead my own research lab at a university. And I just applied to a bunch of places, and Tufts was the best place that gave me an offer. So I'm like, yep, I'm going to go here. So for me, actually, teaching is very beneficial to my research and engineering work, because it enables me to teach my students what I want them to know so they can do science and research in our labs, right? So in some sense, I've always actually even in graduate school, I've done some teaching. People seem to like me as a teaching assistant. So I figured, okay, well, at least I get to enjoy this as well. But I would say that still most of my job is still research. The difference is that now I'm the professor in the lab versus before I was either the student or the postdoc or the staff. So I think that's the biggest change, really.
Every time, like, how often do you feel like you receive new information when it comes to robotics?
New information probably every day. Every day, there's always something new to find. If I want to read a new paper, a new research article about something relevant to our research, I can find one every day. There's probably way too many for me to read. One of the things that we do like to do, especially before COVID, was go to conferences. So the primary venue where people would exchange ideas and talk about their work and give presentations were research conferences in robotics. And there were usually several a year that I went to. And the good news is that finally they're starting to get back in person as well. Just because online it was nice. You could still meet people online, but it's just not the same as in person.
Yeah, it's not the same experience. Also because, networking sounds like an amazing experience.
I mean, networking over Zoom is actually surprisingly difficult, especially for PhD students who just start. So I remember when I was a PhD student and I got my first few papers in conferences, I'd go there and then I hang out, have drinks at the end, meet everybody, become Facebook friends, build up your network around you. You can't really do the same thing about Zoom. So what I'm really happy about this summer is that I finally get to take my students to a sort of a real conference experience where hopefully they have just as much fun as I did when I was at their stage.
And I wanted to ask you, since we have you here, Doctor, I wanted to ask you about, I was reading an article actually earlier, and I was really interested, but I didn't quite understand how did robots relate to psychology. It was something about behavior or, something like that I did not quite understand. So how is a robot, related to behavior, and how is that related to human psychology?
Very, very good question. So there's several ways to think about this. So someone who may be neuroscientist may look at, well, let's try to build an artificial neural network that's in some way similar to the neural networks we see in nature. In practice, I would say our artificial neural networks, so people have heard the terms deep learning, are still very different and fundamentally different from how our brains are organized. On the other hand, psychology sometimes provides insight into the mechanisms by which we learn. So one of the most famous psychologists in history is Piaget, who studied, child psychology and the child developmental stages. Of course, he's wrong on many accounts because he did his work quite a long time ago. But for example, he discovered one mechanism called a circular reaction. So what is a circular reaction? If you give a baby an object like this, the baby may discover that this thing opens. And when the first time they discover it, they'll keep doing it just to see, oh, can I make it happen again? Can I make it happen again? And we may think it's a silly thing the baby is doing, but it's actually very important mechanisms by which we, from a very early age, learn how to manipulate the world around us. We learn when we notice when we cause some change in the environment for the first time, and then we really try to reproduce it as to learn, what did we actually do to make it to happen. So this kind of insights and mechanisms, sometimes we can then take it into a robot and say, okay, now I want to have a robot also learn how to manipulate objects, and I'm going to follow some of the same principles that I think humans are following when they learn those skills.
And how long does it take for, to start that process from zero, to program a robot in order to make him understand?
So we're lucky that I'm not doing this on my own. There's a whole community of thousands and thousands of other roboticists who are looking at similar problems. We're all trying to make our robots a little bit smarter, a little bit more adaptive. So typically when a new robot arrives in the lab and we have to put some software on it, we don't have to write that software all from scratch ourselves. We can usually, there's a community, we can find some software that's already been written for this robot, and then we build on top of it. So people build on top of each other's work, release that in the open source community, and so on until you have some pretty complicated systems that, it's hard to say there's no individual author of those systems, but a lot of people have contributed. So that's the good news for us, is that we don't build those things from scratch.
Oh, that's really interesting. Okay, I didn't know. I feel like, you cannot start a robot from scratch, but at the same time, you do need a lot of people in order to build a really complex robot, right? And how can you make them identify objects, like, okay, this is blue, or this is red, or this is yellow, like, how do you make him understand that?
How do we make robot recognize things?
That's a word. Yeah.
So robots are, like you said, they're very complicated, and there's really a job for everybody. And that's why oftentimes our students who work in the labs are a combination of mechanical engineering, computer science, electrical and computer engineering, because everyone can contribute something. For the question of recognizing objects in an image, so people have, even since the 80s, there've been a variety of solutions. A lot of the more current ones work with neural networks. So neural networks that try to identify, train on very large corpuses, very large data sets. Imagine you have 1 million images of cats, 1 million images of dogs. When you provide that with the label to a neural network, you can train it to recognize, given a new image, is it a cat or is it a dog? Now, the challenge with a robot, of course, is that we can obviously try to find data sets from the computer vision community, but the robot itself may sometimes need to say, well, what is this new object? I don't know what it is. Has to go ask a human, have the human tell the robot, what is this object, and really learn things through interacting with humans. So that's some of the research that we have done, especially when I did it as a postdoc at UT Austin, was if a robot sees a new object, it sees it as an object, but it doesn't know what it is. It can ask a human, give me some words that describe this object. And the human may say, well, it's teal colored, it's a coffee cup, it's full, which I can only tell it's full because or half full because I can feel the forces. So there's a lot of multisensory perception that comes in here. And so a lot of our work is focused on how can we get humans to teach robots to essentially recognize the language about objects in their environment, which is really, really amazing in my opinion.
Wow. I mean, and how many people do you have at your team? Like, is every student, in your case, specialized in every single part of the robot?
So one way to think about a PhD is you look at incredibly deep into a topic, but the topic becomes very, very narrow. So usually every PhD student kind of has a focus on, I want to do this. I have one student, for example, who wants to use augmented reality to improve human-robot collaboration. That's good. I have another student who's looking at how can robots learn sort of using all the sensory modalities like vision, touch, audio, and fuse them and learn from one to others. So they're very different pieces that each student sort of picks to investigate. My job is to sort of tie it all together and sort of say, well, here's a robot that can interact with AR. It can also learn to interpret, a variety of types of signals and connect them to the objects around it, and so forth. So usually everyone would have sort of their own topic of research, which eventually becomes a dissertation.
Okay. Sounds good. Sounds good. Sounds like it is a lot of work. And okay, we understand how big of a project it is to build a robot to complement the robot that it already exists. But talking about money, how affordable it is to build a robot?
How affordable it is to build a robot. So luckily, most of the time, I don't build robots from scratch. We just purchase them whenever we can with funding that we have. So they're a lot cheaper than they used to be. So when I was a graduate student, the robot arm that I worked with, it cost about $135,000 for one robot arm. Yeah, I know, jaw. I think the hand of the robot itself costs like $25,000. So one time I was holding the hand and I dropped it and I'm like, oh my God, it's like dropping a Ferrari, right? Something like that. But anyway, the good news is that the cost has gone down. So in terms of, especially in educational robotics, a lot of the work we do, especially in our classes where we want to introduce students to robots, we can only give them the most expensive robot, but now some of the educational robots are under $1,000, under $500 and so forth. And some of them can do very fancy things, or at least you can still prototype machine learning solutions, artificial intelligence solutions for them, but they have gotten cheaper. In terms of a career-wise, usually if somebody becomes professor in robotics at a university, the university will dedicate some amount of money and say, this is your startup equipment money. You can now spend this money over the course of the first few years in your career to build up your research lab with robots and hardware. And usually after that, we have to write grant proposals. So if a lot of the research is funded by federal government funding agencies, and sometimes there you can budget in money for equipment if the project requires you to buy new equipment.
And let's say, talking about experiences, what has been the biggest technical challenge you have ever solved when it comes to building a robot?
The biggest technical challenge. So again, I wouldn't take all the credit for this because there's no way I could take the credit for teamwork by myself. But I'll say some of the most impressive thing that we have done in the past was when I was at UT Austin as a postdoc, we had robots that could essentially drive around in human environments and not hit anybody, be able to go essentially localize their environment, map their environment, and be able to perform simple tasks like object delivery or delivering messages or guidance. So this was a big project at UT Austin. And I would say in terms of a technical, especially an engineering accomplishment, in terms of actually building a system and having it work in a physical world as opposed to a virtual world on a computer, that was probably the most impressive thing. And it was kind of the hardest thing because, it's like imagine driverless cars. Now, driverless cars, of course, it's difficult to make cars drive autonomously, but at least there are lanes. At least there's some rules that other cars will follow. But if you're a robot driving around on a Segway in let's say a big convention where people are just going all over the place, crossing each other's trajectories, there's no rules. And making sure that my robot doesn't hit anyone was definitely a challenge, but we made it happen.
You made it happen? Do you have any video or something like that from that?
So if you go to my website, or if you just Google my first name, Jivko, you should be able to find me on YouTube. There's lots of videos. There's lots of videos of that kind of research there and about the research as well. And on my website, of course, there's if you find my website by searching for my name, you can obviously find some videos there. I'm lucky that in terms of my name is so rare. Jivko, just put the first name in Google, I'll show up. I should be the first one as long as you're searching from the US.
Yeah, that's true. That's true. Especially, I mean, I'm pretty sure that people will love to see the visuals of your experience,
Mm-hmm.
And okay, we've talked about your experience, your professional experience, some robotic experiences as well. But I wanted to ask you, how do you think that kids nowadays can learn about robots?
Very good question. I'm glad you brought this up. I don't know if you actually looked this information, but we do have a project funded by the NSF specifically at how do we teach AI to kids with robots. And sort of one of our central hypotheses is that if you let kids really build up the robot, and then even before they learn how to code it, to learn how to interact with artificial intelligence. So get the idea that, I can build my robot and now I can train my robot to walk, for example. So one of the projects is the kids build the robot, then they train the robot to walk using positive and negative feedback. So essentially, they don't know how to code the AI yet because they're too young to know how to do that part, but they can at least get into the mind of interacting with a machine learning system. So oftentimes when you're trying to train a robot to do something, you would provide negative and positive feedback based on what you observe it doing, and the program will try to remember what to do in the particular situation. So in one of our projects, we actually have we actually are dropping robots off to kids, having them build them, and then having them train their robot to do particular things. And it's actually really amazing. So we did a study where during the COVID of all times, we send the robots to kids in their houses. We connected over Zoom. We had the kids build the robots, and we had the kids train the robots. And the most amazing thing I saw from that experiment was that when we asked one of the kids, how should the robot learn about its world? Should it mostly try to do exploration where it does new things it hasn't tried before? Or should it try to do what it already knows how to do? And the kid said, well, actually, initially, it should be the first, try to do random things and not do the things that it doesn't know how to do. And then gradually, it should start to doing the things that it thinks it knows how to do, which in machine learning, there's a very technical term for this called epsilon decaying exploration, which somebody had written a research paper about maybe 10 years ago. But this kid came up with the idea on their own, which was just amazing. So we're continuing to engage kids in this work. And we'll see how it goes. We have about 2 more years of this project left.
At that age, at that specific point of their lives, do they understand the difference of cognitive data with a robot and sensory, or is there a difference there?
I see. That's a good question. So usually kids start when they first start programming robots, it's usually the Lego robots. And usually they say, okay, I'm going to read the sensors, and based on the sensor readings, I'll make my robot do something. Maybe go forward, maybe turn left or turn right. It takes a little bit for them to think about, we can take the sensory data and then do more complicated things with it. So at that age, probably not so much, but I would say the kids who did interact with the learning robots and were training the learning robots, they did come up with some kind of a mental model about there's more than just, direct responses to sensory data. The robot, maybe it's doing something a little bit more complicated than that. But it probably takes a little bit more time to get there. Ideally, I want to get to a point where kids can come into college, and in their first year, they can take an advanced artificial intelligence class. so they can immediately start thinking about cognition from a robot's point of view. We're not quite there yet, but we are getting there.
But and that's another question. We are getting there. I mean, since you're saying that robotics is a non-stop experiment, if you can say it like that, I mean, I think that nowadays it's like a way of living. How do you think that, no, when do you think, that's a question. When do you think that we can totally implement robots into our lives?
So fully integrate robots into our lives.
That's the word, yeah.
It's hard for me to answer that question because, of course, some of us want it to happen sooner than later, but of course, many people have made these kind of predictions of when. And if I look at when I was a kid and reading predictions by 2020 was supposed to have happened. So I think we also have to be careful that perhaps full integration is not exactly what we're aiming for. There are many reasons why you may want a robot in your house to help you with things, but there are many reasons why in some situations you may not necessarily want a robot in your house. I think the integration will be a little bit more gradual in the sense that we're going to get to more and more robots that are a little bit more versatile and can do a little bit more than just one thing. Many of us have a Roomba or a robot vacuum in our house, and it does great things, but that's all it can do. I think the next step and the next leap forward will be when we have a robot in the house that can do more than one thing, and that also can get out of the way when we don't want it to be there, because I think that's also important for humans in terms of from privacy and other ethical standpoints to make sure that we don't necessarily want a robot to be always there, always on, always watching you. For some people, perhaps that's not okay. I think some of the most important applications we're looking at, another application where we think that integration is happening is people with disabilities. So we recently received a large NSF grant called Mutually Assistive Robotics, where we'll develop the algorithms that enable, so if you're a disabled user and you have a robot, let's say a robot arm to help you pick up things from the ground or even feed yourself, sometimes those robots, they're delivered by a company and they have a very fixed set of functions they can do. And maybe for the particular user, it doesn't work very well. So we're trying to develop algorithms where the human can essentially help retrain the robot to do things the way the human wants them to do. And also where the robot can actually sort of help the human learn how to use it better. So it's called mutually assistive robotics. So I think in the area of interaction with people with disabilities and motor impairments, I think there we're already seeing sort of the tightest integration between humans and robots.
Oh, I love how inclusive even robotics can be. And any last advice that you could give to our audience about robotics, about your personal experience, any helpful advice that our audience would love to hear?
I know it's very, very cliche, but keep trying even if you fail, because we will fail. And I've certainly failed at many things. Many things did not work. In fact, most things you try when you're doing engineering and science do not work. That's in terms of doing the science. In terms of trying to get into a career in those fields, I know sometimes it feels like it's a little rough, but it has become a lot better than it used to be. So again, keep trying, regardless of how much you fail, keep trying, and eventually you will discover what drives you and what makes you happy professionally wise. So it's kind of a lucky position to be in, where I'm doing exactly what I would want to be doing, which I know it's hard. It's hard to get these days, but in science and engineering, at least it's possible.
Thank you so much for being here. We were super lucky to have you. And do you have any social handles? I know that you mentioned that you have a website.
So my lab has a website. It's called mulib.cs.tufts.edu. Or you can just, again, Google my first name, Jivko, Jivko. You might find me on YouTube and other places, and you immediately get to my website. And by any means, get in touch if you have any questions about the work that we do. Or if perhaps you're an undergraduate student thinking about graduate school, we're always hiring. We're always trying to accept more PhD students into our program. So don't hesitate to reach out.
Oh, thank you so much. That's lovely, Doctor. Thank you so much. And remember, guys, that you can also find more information and interviews, really helpful interviews like this one, directly on our website, controlhub.com/builder-nation. We would love to hear from you as well. And thank you so much for being a part of this community. We're super, super lucky to have you, Professor, and hope to see you sometime soon.
Thank you. Thanks so much for having me. Bye, Alyssa.